from the University of Padua. During his career, he has been a researcher in different institutes, including University of California in San Diego, Jet Propulsion Laboratory, Caltech, and Harvard. His research focused on understanding the origin of the stars, and his works involve mostly numerical simulation of magnetic hydrodynamic turbulence. Welcome.
Okay, thank you very much, and thank you for the opportunity to present my work here. The purpose of this is primarily to talk about a new paper that I'm submitting together with Mark Giles, who is in the audience, about H2 regions. And but in order to do that, I need to talk about it doesn't go to the next. Okay. I need to talk about the origin of massive stars, which is a paper that I published in 2020 with these other people here. And so this is actually a talk about star formation in general, but particularly high mass star formation. I probably don't have to tell this crowd why massive stars are interesting. They do a lot of things in galaxies, in the universe, but what I want to say is what I mean by star formation. And when I think about understanding star formation, I think about understanding how how a star is assembled. Where is the gas coming from that goes into the star? What are the pathways, and how long it takes to get there? And for mass, and then of course you want to understand the IMF, the mass distribution of stars, and the star formation rate. But for massive stars, there is another key question, which is what is the biggest star you can form as a function of the environment? And that's important if you want to understand, for example, the higher HII universe, because it seems like you need very massive, maybe extremely massive, maybe supermassive stars to understand chemical anomalies, like in globular clusters, for example, or also in the first galaxies seen by JWST, or if you want to form the seeds of supermassive black holes as well. So, how do we understand stellar masses? Well, in a typical star-forming clouds in our galaxy, the GOS mass is of the order of a few solar masses. But the stars have this broad mass distribution. There are stars of all masses. And so how come that the characteristic mass is actually much smaller than the GOS mass? Clearly, you need some sort of fragmentation. And in the last 20 years, we have studied supersonic turbulence, and we understand that we have what we call turbulent fragmentation, meaning that the turbulence create a log normal probability distribution of a broad probability distribution of gas density. Basically, it fragments the gas. And if you have very high density locally, then the Bonner-Ebert mass locally can be very small, and so you can form small stars. And we think that the characteristic mass, the peak of the IMF, is essentially the average GOS mass divided by the RMS Mach number of the turbulence. But what about massive stars? So you have to be able to form stars that are much more massive than the GOS mass. How do you assemble multiple GOS masses? That's not an easy problem. And the proposal was in 2002 and 2003 by this famous paper by McKee and Tan that a massive star comes from the collapse of a massive core. And the reason why you have a core that contains many GOS masses is that because you have not just thermal pressure support, but also turbulent pressure support. If you believe in that turbulence can provide a source of pressure support, then you think that maybe we can have very, very massive cores, and then the star forms very rapidly in a collapse time. So 100,000 years, you form a massive stars very rapidly. Problem is that 25 years later, now we understand supersonic turbulence, and this core, of course, the turbulence has to be supersonic because you are providing support on top of the sound speed. on top of thermal pressure. And so these cores would actually fragment. You cannot have a core that contains multiple GIMS masses because of supersonic turbulence and not have internal fragmentation. And the other problem that is more fundamental is, okay, but how did you get the core in the first place? How do you assemble that core? So you haven't really solved the problem. You have to explain how you form that core. And then the other problem is that these cores are not really found by the observers. I mean, okay, there are some massive pre-stellar cores, perhaps, but they're very rare. They're very difficult to find. They're not there. What I proposed in 2020 was a different scenario of how massive star forms that we call the inertial-inflow model. And basically, the point is that we're thinking of turbulent fragmentation usually, but really turbulence is always accumulating stuff, and we're in random places. It's supersonic turbulence, so some velocity field is shear motions, some motions are expansions, some other motions are compressions. And so there are random compressions in supersonic turbulence. And so you can accumulate mass locally. Sometimes you accumulate a little bit and you form low mass stars, and sometimes you accumulate a lot and you form a massive star, and it's totally random. But the point is that as you accumulate, as you bring mass to a certain point where you're going to form a star, when you reach a GIMS mass, basically the core will collapse. And so the idea is that you don't actually form very massive pre-stellar cores. And so there has to be growth after the collapse. The turbulence brings mass to a certain location where you form a star. You form a core that is a few solar masses, you form a star that is a few solar masses, and there has to be extra growth after the collapse. Because the turbulence flow is still bringing mass there. It doesn't care that the thing collapsed, it's still bringing mass there. Okay, this is just to show that ALMA surveys indeed show that normally you don't find very massive pre-stellar cores, like 100 solar masses pre-stellar cores. If you find massive cores, they tend to be protostellar. And actually, the mass distribution of protostellar cores is typically shallower than the mass distribution of protostellar cores. So this is the idea of this new idea about how you form a massive star. Basically, you have actually all stars form at the intersection of filaments. In supersonic turbulence, you have shocks all over the place. And the shocks form dense, the intersection of shocks form dense filaments, and the intersection of filaments form cores. Some cores will be small, and you just form a low mass stars. Some cores can become really massive, in principle, but that's after they have collapsed. Because it just happens that locally you have denser filaments, longer filaments, you can accumulate more mass in certain spots, and that's where you form a massive stars. On small scales, of course, the velocity is controlled by gravity. There is infall, and then you have an accretion disk eventually onto the star. But the point is that what brings the mass there is the large-scale flow, and the large-scale flow is not dictated by the gravity of the star, it's turbulence. So that's why we call them inertial inflows, because these are supersonic motions that are not responding to the local gravity. They're just turbulent motions. This scenario was not taken out of thin air. It's actually inferred from a gigantic simulations that took me 5 years to fully develop. And it's a very realistic simulation of star formation at 250 parsec scale, where we resolve the formation of individual massive stars. We follow the massive star until they explode as supernovae. We have hundreds of massive stars, hundreds of supernova explosions, and the turbulence is driven by these real supernovae. Okay, I'm going to show you only one plot from that paper, from that simulation. And this is, I think, the most important plot in star formation, the way I view star formation nowadays. This is how long it takes to form a star, TF, in mega-year, versus the final mass of the star in solar masses. And these are stars from the simulation. And you can see that there is a gigantic scatter, but on average, it takes longer to form a more massive star than to form a low mass stars. And when you fit this large scatter, you get this relation that the time to form a star grows like essentially the square root of the final mass. And these are million years. So to form a massive star, it takes 1 or 2 million years in the simulation, not 100,000 years, like in the Tan and Key model, the collapse of a core. More importantly, there are two well-defined envelope, an upper envelope in the scatter plot and the lower envelope. The upper envelope is easy to understand, is the outer scale of the turbulence, the dynamical time of the turbulence. The size of the system divided by the RMS velocity. The lower envelope is time that scales linearly with mass, is a constant accretion rate, is the maximum accretion rate that you can have in that particular turbulence simulation. And what is the maximum accretion rate you can have? The best situation would be that you have a cloud and the whole thing goes into a single star in a dynamical time. M is the total mass of the system divided by the dynamical time of the system. But because this is turbulence and the velocity field is random, you can never have the whole cloud collapsing onto a single star. Only a fraction of that can collapse onto a star, and this is epsilon, which is probably just a geometrical property of turbulence, a universal constant. And so, all the stars are between these two envelopes because you cannot accrete faster than that, and you cannot keep pushing things into the same point for more than a dynamical time because it's a turnover time of the turbulence. After that, the velocity field is completely different. Turbulence keeps resetting itself. So you cannot have convergent flow to a single location, to a single star for longer than that. The intersection of these two envelopes defines the maximum mass that you can form in a turbulent flow. And here you have your very simple model for what is the maximum mass that you can form, the most massive stars that you can form. And if you look at these two equations, these two formulas, you find that the maximum mass is just epsilon times the mass of the cloud. So the maximum stellar mass you can form in a cloud is the mass of the cloud divided by 500, essentially. Okay, as simple as that. So this is a summary of what I just said, essentially, that comes from the analysis of this big simulation. The formation time is mass dependent. It scales like essentially the square root of the final mass, so alpha is about 0.5. Time 0 is a normalization. It's a slow process. It takes of the order of mega years, not 100,000 years. And there is a maximum mass that you can form, which is essentially the mass of the whole system times 2.5 10 to the 3. And we think that this is a universal sort of efficiency, if you like. Okay. More importantly, not more importantly, also importantly, if the maximum mass is set by the cloud mass, now think about the whole galaxy. When you form stars in the galaxy, there are clouds of different masses. And in fact, we know that star-forming clouds have a mass distribution with the exponent, I call it beta cloud, which is about -2, roughly. In external galaxy also, we find this. So a big cloud, this is the Salpeter IMF for a single cloud, just a power law. A big cloud may form stars of 300 solar masses. A smaller cloud maybe will stop at 30 solar masses. So clearly, the field IMF, which is a collection of many clouds, of star formation in many clouds, will have to steepen above a certain mass because here up to here, every cloud is able to form stars up to this mass. But then you have to account for the mass distribution of clouds, and so there's going to be a steepening. I think this is something that was not predicted by other models before, so it's kind of a new thing that the field IMF has to have two power laws, essentially. Has to have some steepening, and the steepening depends on the mass cloud distribution, but essentially you go from Salpeter 2.3 to 3.3. It's a significant steepening, okay, with a realistic beta of 2, for example. So, how do we test this model? So, is really star formation so slow? Does it really, is the formation time really depends on the mass with this exponent? Is there really a maximum mass and therefore a steepening of the EMF? How do you test that? In a sense, observers have already been discovering this inertial inflow model independently, because what you find observationally is that massive stars are formed in regions that look like what they call hub filament structures. So basically the intersection of filaments where the mass is coming into the system through these filaments. And so you can see that there is a mass reservoir at large scale that feeds the formation of massive stars. And you could say, well, you're just feeding a cluster and you're just forming new stars. No. You're actually feeding individual stars because, as I mentioned before, we also know on small scales that the protostellar cores are more massive than prestellar cores. How come that the cores are more massive after the star has already formed? Clearly, it means that even at the level of individual star, you keep feeding the core and presumably the star. And so this is exactly what I'm telling you, that there is that is a slow process because the mass reservoir is at large scale. I mean, it has to be a large scale because you have to put together 100 solar masses where it has to come from large scale because you need a lot of mass. But you can do better with the observations, and that's the topic of this paper, which is the topic of the second part of the talk now, which is you can use compact H2 regions. And by the way, you're welcome to interrupt me, questions, comments, okay? Anybody? Why do we think that H2 regions are important here that can help? Because this is a cartoon of what happens when you grow a core. So this is time, and this is just a cartoon, it's not a realistic picture. And this is the mass of the core. So initially, you form the core. When the core reaches the Jeans mass, it collapses, it forms a star. And then the star has to grow. And I told you the growth time is a couple of million years, maybe. But the core also grows, keeps growing. The turbulence is still bringing mass. The turbulence is still bringing mass locally there, okay? But look, but what's going on? I shouldn't touch it, maybe. Okay. So, but what you see is that during the period of time where the star is formed, now you have not a protostar, you have a star, because this is a long time, and the Kelvin-Helmholtz time for intermediate mass stars or massive stars is short. And so you have a main sequence star that is growing. What's going on? You have a main sequence star that is growing, and that star is ionizing the gas around it. But you also have a lot of dense gas that is accreting from the larger scales. You have a compact H2 region, okay? So what we're saying is that a consequence of this inertial inflow model is that the growth of the star is accompanied, you have a coexistence of the growth, the stellar growth, and the ionization. And so you have basically a compact H2 region for the duration of the growth. So if you can measure the lifetime of compact H2 regions, you constrain the growth process of the star. That's the idea, okay? And well, people tried 35 years ago or more to measure the lifetime of H2 regions. And in fact, it was a problem. It's a classical lifetime problem of H2 regions. That was discovered by Wood and Churchwell in 1989. They found that there are too many compact H2 regions in the galaxy, too many relative to the number of massive stars. And because a stronger sphere that expands in a uniform medium, it expands at the speed of the ionized sound speed, 10 kilometers per second. And if we define the compact regime anything below 0.1 parsec, that takes 10 to the 4 years for an expanded ionized bubbles to reach that size. But the number of H2 regions they found, divided by the number of massive stars they found, multiplied by the mean sequence time of the star, gave a statistical demographic timescale of 10 to the 5 years, 10 times longer. This was famous lifetime problem of H2 region that has been there forever, except there have been a lot of papers saying, well, the H2 region is actually confined by this or by that. There have been a number of papers to try to explain why it takes longer for this H2 region to expand. Okay. Anyway, there are very large uncertainties here because you understand that OB star go from a few solar masses to 200 solar masses, so the main sequence time varies a lot along the masses. So the uncertainties are very large, and the uncertainties because you're also counting things in the galaxy is not easy. Well, in 2018, Motra Metal improved the exercise, and they said, yeah, let's count the number. Let's divide the number of compact H2 regions by the number of OB stars, and then multiply by the mean sequence time to get the lifetime of the H2 phase, of the compact H2 phase. But let's do it in luminosity bins, because then if I fix the luminosity, I know the mass of the stars and I know the actual mean sequence time. So it's a much more precise exercise. And I'm comparing apples with apples because I'm comparing, this is the luminosity function of OB stars. And this is luminosity function. So this is number, density of objects versus luminosity. And this is the luminosity function of H2 regions. Well, they just confirmed within Churchwell. Okay, so 20 years later, same answer, about of the order of 10 to the 5 years. And still nowadays you see papers. So this is the state of the art. So from 30 years ago, but it's still the state of the art. So people nowadays, for example, try to measure the statistical age of the protostellar phase of hot molecular cores, for example, using this as the reference age. So people really are using this number. It's not like it's been forgotten or anything. And then you can decide whether there is a lifetime problem or not anymore. But the point is that in principle, you can do this demographic exercise and try to extract the age of the lifetime of H2 regions. There is an assumption here, which is the McKean and Tan model, that the star forms in a blink. And so you have a star that is already formed, that has already reached the final mass when it starts to ionize. In my way of forming a star that takes longer, that's not the case. And if the star has not reached the final mass, if the OB star that reaches the final mass that gives this final luminosity, when it was ionizing, it was still growing, so actually had the lower luminosity. And that means that you have to compare this number with this, not this with this, and that will give you longer age, at least by a factor of 2 or so. So you can already appreciate that if the star is still growing while it's ionizing, it has on average half of the final mass, so maybe a quarter or an eighth of the luminosity, and therefore you have to compare different luminosity bins in the two luminosity function, and you get a longer time scale, a lifetime of H2 regions. In reality, you have to do the exercise much better, and I'll tell you why, okay? But the point is that now we have to redo this exercise with a realistic model of star formation that is not star form in a blink, stars form in maybe a million years, or star form with some law that I want to see if it's correct or not. And I want to use the luminosity function to test it. So this is the, classical picture. You form a star immediately. So the H2 region is powered by a star that is already the final mass, and so the same luminosity as the optically revealed OB stars. In my new picture here, is different because the star, as it grows, is smaller initially, and so the luminosity is smaller. And also, this is the longer lifetime. And so you have to compare the two luminosity function more carefully. Okay. So how do we use H2 regions as clock properly for star formation? These are track of, this is luminosity. You can think of growing mass as well versus time. So this is a star that ends up being 7 solar masses and one that ends up being 30 solar masses, for example. And once they stop growing, the mass is constant, the luminosity is constant, well, constant, it's in the main sequence. And you know that, it's easy to go from an IMF to a luminosity function of OB star. So the way we model this is with a numerical model with Monte-Carlo sampling. But first, I want to give you the analytical flavor of the model. So the point is that you start with a simple IMF, which is a power law. Think of salpeter IMF, m to the power minus 2.35, okay? Just a single power law. You can easily derive the luminosity function for field star, assuming constant star formation rate, for example, from a given IMF. You only need to do stellar evolution, essentially. You need to have a mass-luminosity relation. You have to turn masses into luminosity, of course. And you assume it's a power law with exponent gamma. And you need to know the main sequence time, because you need to know that these stars doesn't stay alive for a very long time, while low mass stars, there are more of them, plus they live longer. That's why the luminosity function, which is now upside down, this is luminosity and this is number of objects per volume. That's why you have a luminosity function that goes down as you go to more massive stars. And you can work out the exponent. The exponent of the luminosity function of OB star is 1 minus the salpeter exponent minus delta divided by gamma. This is the stellar evolution, okay? How do you get the luminosity function of H2 regions? Well, it's a similar exercise. You start from the same IMF, and you need to know how long it takes for a star to form, because we said that as the star growth is ionizing the environment, so the compact H2 region lasts roughly the time of the growth of the star. And so, for example, the star, this OB star here, while it was growing, typically it has half of the mass, statistically, that it had at the end, and so the typical luminosity will be this one, and so it maps here in terms of the luminosity function of H2 regions. But look, there is another problem, another complication, that there are stars that will become much more massive, but initially they also had the same luminosity because they were also at lower mass initially. So a luminosity being in the H2 region luminosity function has contribution from stars of different masses. So that's why you have to do this convolution, okay? Anyway, you can do it analytically if you start with a simple power law and you find that the exponent of the luminosity function of compact H2 regions in this model will be given by 1 plus alpha and then minus the salpeter exponent and divided by gamma. So here you see that because you have to use a law for the formation time for the duration of the H2 regions, which is the law that we borrow from the inertial-inflow model, that alpha now enters the slope of the H2 region luminosity function. And interestingly, if you take the difference of the two, what is the difference in the slope between the two luminosity functions? As the salpeter slope cancels out, the IMF has nothing to do with that, which means that even if you don't know the IMF, if you're able to observe the two luminosity function and compute them and take the difference of the exponent, you're already constraining alpha. You're already constraining the exponent of the growth law of massive stars. That is a lot of information there. Okay. The time scales depends on the normalization as well. So the idea is that we can improve the exercise Motra-Metal comparison of the luminosity function now. We can do it with assuming this growth law instead of a star forming a blink. But also, that was 2011. We're not going to use the same luminosity function as in 2011. So we were a little bit more ambitious, even if we're theoretician, and we thought, okay, let's get, first of all, the best luminosity function we can get. And for the H2 region, we use the same as in Motra-Metal, the RMS survey, except the Motra-Metal was 2011, the RMS catalog was finished in 2013, and it has been maintained since then. And so we have more sources than were published in Motra Metal. So we have an improvement there. We have over 800 H2 regions in this luminosity range. And so we built the luminosity function based on that catalog. We didn't really have to do much there. For the OB star, we're also lucky because there is the new release from 2025 of the ALMA Luminous Star catalog by Pantaleoni and Gonzalez, ALS-III, and which has basically all the O stars as spectra from the GOS catalog, I think it's 2024, sorry. That's also new stuff, 2024. And then we and so now we have basically a luminosity function with almost 10,000 objects in this luminosity range. And I can give you more details about how we do that. But the point is that it's much better than what was available in 2011. This is post-Gaia, so we have distances for the stars. And in Pantaleoni and Gonzalez, in ALS-III, the distances have been improved, the photometry has been improved. As I said, we have spectra for all the O stars, etc., etc. So we can we compute the bolometric luminosity of the star. Is still non-trivial because you need to know the effective temperature, which ideally should be based on a spectrum. And then you need good bolometric correction to go from the G magnitude to the bolometric luminosity. But there's a way to do it. And then you have to make completeness corrections for your catalogs, which we do. And then you have to compare apples with apples, which is non-trivial because with the RMS surveys, which is these are H2 regions found in the far infrared based on the colors, not in radio frequencies, okay? But it's so good that you can basically see H2 region in the whole galaxy. This is the blue is this is heliocentric distance, and this is the number density of sources of H2 regions. With OB star, it's not so easy. When you go a few kiloparsec away, then you start to lose them. You see the number drops. So you have to make sure, and also this is the galactic distribution. This is galactocentric distribution. And you see that H2 regions, there are more H2 regions when there is more gas. It peaks at around 5 kiloparsec. For the OB star, they peak at 8 kiloparsec. Well, you can guess why, because we are at 8 kiloparsec and we see mainly OB stars around us. So you have to make sure that you compare apple with apple, and then you do that by renormalizing slightly the H2 regions to account for the fact that most of OB stars come from here, so you have to lower the normalization of the H2 region a little bit. Okay. This is in my opinion, state of the art, but you can probably do better, luminosity function of OB stars in our galaxy based on the ALS-III catalog. This light gray symbol is the one from Motra Metal 2011, which was actually read 2005. So you can imagine that 20 years later we go from 500 stars to 7,000, and this luminosity function is it's much better, of course. And the dashed lines are the prediction of the analytical model that I showed you earlier on, based on a salpeter IMF, essentially, but also with the steepening. So if you try to fit this luminosity function with one power law, and you get a chi-square, and then you fit it with a broken power law, like we do here, so basically one slope, another slope, and the knee mass in the middle, you prefer the broken power law fit relative to the single power law fit with a significance of more than 7 sigma. So the field IMF is a broken power law, period. But I don't think it was known before we did this exercise. And more importantly, it was not predicted, but the model I showed you before does predict that it should be a broken power law, because the maximum stellar mass you can form is a linear function of the cloud, of the mass of the cloud where the star is formed. But the normalization, and actually the slope even, you could already see in 2005 that it was a broken power law, honestly. Although Motra Metal, they fit it as a single power law. And the knee is about 25 solar masses, meaning that the smallest cloud where you can form star is 10 to the 4 solar masses. which is a good estimate because you know that in our galaxy, at 10 to the 3 solar masses, most clouds have large virial parameter. They're not forming star effectively. And this is our state of the art for the H2 region luminosity function, the compact H2 region luminosity function. Again, we're very close, of course, to Motra Metal because it's the same survey just a few years later. And notice the slopes are shallower as predicted by the analytic model I showed you before. They're shallower than the, 1 and 1.09 and 1.6. And here is 0.2, 0.3, and -1. They're shallower as it should be. And the slopes are also predicted roughly by the analytical model. And look at the knee position. Again, more than 7 sigma significance that there are 2 power laws, not a single power law. But look at the knee position. Here it is at 10 to the 5, and here it is at 10 to the 4.6, lower luminosity. And that's what I said before. In this model, you have growth during ionization. So the stars, when you go from the luminosity function of OB star to the luminosity function of H2 region, you have to map to lower luminosity. And in fact, the knee has a lower luminosity in the H2 region luminosity function, as expected. Anyway, you have to do this numerically, not just analytically, because you want to have a handle of the uncertainties, and you really want to constrain the growth law. And you need to know the actual normalization of the 2 luminosity functions. So, but it's the same story. We start from a broken power law IMF, and if we do stellar evolution now with these silly power laws, but with the stellar evolutionary tracks, with the MIST tracks, the MESA tracks, and you assume a growth law. So just from the track and from the IMF, you can immediately derive a model, this time numerically, sampling masses with Monte-Carlo sampling, a model luminosity function. So, and then you compare, and also a model H2 region using a growth law, like I said before. But then you have the observed ones that now have been highly improved. And so you have to, that will constrain these ones. So by fitting the model luminosity function, which comes from the IMF, to the observed luminosity function of OB stars, you fix the IMF. So you constrain the 2 slopes of the IMF and the mass of the knee. And then when you fix the IMF and you apply this growth law, you find the model H2 region, and by comparing the model H2 region with the observed one, you're going to constrain alpha and tau naught, the growth law. And now you constrain the growth law by the comparison. Okay. Each of these 2 has its own chi-square, and so you can then measure the uncertainties. And what you find is alpha of about 1/2, and tau naught, which is normalized at 60 solar masses in this case. At 60 solar masses, it takes 2 million years to form a massive star, based on the comparison of the 2 luminosity functions. And this is the fit. We adjust one model, one single IMF with these 2 power laws, and with just that and the growth law, you can explain very nicely the shape and the normalization, of course, of the OB star luminosity function, and at the same time of the H2 region luminosity functions, and the 2 knee, the position of the knee, the relative position of the knee at the same time as well. And this is for the best fit parameters. What are the uncertainties? Well, when you fix the IMF for a given IMF, and then you do the exercise of fitting the H2 region luminosity function, this is what you get. At the this is the 3 sigma uncertainty or confidence interval. But then, because you have a chi-square that comes from fitting the IMF to the OB star luminosity function, you can generate many IMF and repeat the exercise of fitting the H2 region luminosity function. And so you propagate the uncertainty in fitting the IMF into the uncertainty for alpha and tau. And so, of course, the uncertainty are growing now because there is some uncertainty in the IMF field. But listen, even at the 3 sigma level, the alpha has to be between 0 and 1, which is what I told you initially when I showed you the scatter plot from the simulation. Alpha has to be between 0 and 1, which was the maximum star accretion rate. And on average, it's about 0.5, and well, the best fit value is 0.5, and the formation time is mega years. Okay. So, in conclusions, the lifetime problem of H2-region is not a problem in the context of a realistic star formation scenario where massive stars don't form suddenly, but they take some time to form, and as they form, they ionize the gas that is accreting, that is actually making them grow. And then the comparison of the two luminosity function, OB stars, and if you do it carefully, OB star and H2-region, is giving you not only the time scale, the lifetime of the H2-region, and so the time scale of how massive star grows, but also the mass dependence of that time scale, this alpha parameter. And it's well constrained. And it's constrained by the relative slope of the two luminosity functions, like I said in the beginning. And then the field star IMF, well, the field star luminosity function is not a power law, is a broken power law, which means that the IMF is a broken power law, the field IMF is a broken power law, which confirms the fact that there has to be, that there is a maximum mass that depends on the cloud mass. And the knee of the H2-region luminosity function has a lower luminosity relative to the knee of the OB star luminosity function, which means that there is growth during ionization. Otherwise, the knee would get the same mass. Well, if we could repeat the exercise in a different environment, we could try to demonstrate that alpha is universal and tau naught instead is expected to depend on environment. You form stars more rapidly in the central molecular zone, or in a starburst, for example, or in a globular cluster, probably, than in the outer galaxy. And to conclude, I'll say that the lifetime of H2-region is most likely longer than the classical number, so that's to be kept in mind. It could be even 10 times longer or it could be maybe a couple of times longer. It depends on the luminosity of the H2-region. It's not a single number. If an H2-region is going to form eventually, and you'll never know when you observe an H2-region, is going to form 100 solar mass stars or 10 solar mass stars, you don't know yet, right? But the H2-region is increasing its luminosity versus time. That's the main evolution of the H2-region. It's not an expansion; it's a growth in luminosity. And the time scale. So when you do demographics, or you try to use the lifetime of H2-region to determine the lifetime of, for example, molecular cores, you have to be really careful. It's not a single number; it is probably significantly longer than the traditional number. And that's it.
We can talk later, but I guess that's
So
one of them was how you mentioned the term with completeness to build this function of this region for all these stars. How well do you think it's taking into account the sense that for less massive stars or less luminous regions are harder to detect observationally? In particular, if you are using infrared wavelengths, so there could be some that are deeply embedded and they are not detected as being the infrared. Then how could this completeness, maybe broadly estimated, affect the result that you're getting? So if you're doing 3D solutions observe it's not like this, but you have more or less luminous object, then it would be more like a single power law. How to this change, or have you explored some option of modifying this distribution, the observed distribution, and
yeah, so far, I mean, we do a completeness correction. We do a completeness correction, which is basically we look at different volumes, we got different distances, and for each luminosity bin, we can see at what point basically you reach a maximum value in number densities. And that's basically the value that we take for the luminosity function. It's actually the value we take for the completeness correction. So it's like a 1 over Vmax method, the traditional method. But really, I think that nowadays, for the galaxies, within a couple of kiloparsecs, I think we are seeing most of the OB stars. And notice that both surveys don't look inside in the central 2 or 3 kiloparsec. So we don't have that problem, except it would be interesting, but it would be a different environment anyway. And so the problems you're mentioning are certainly very important here. But you're right. I mean, even when you go into the outer galaxy, you sometimes, I mean, when you go further from the solar neighbor, you miss a lot of AB star. But I think this is a completeness correct. This is really a flux limit, and this is a problem that, you know, it's well behaved in a sense. Less luminous stars are not visible at larger distances, and so you can do this 1 over Vmax correction that I think it's okay.
I was thinking more for the H2 region, because I like this idea, because I think it's correct this thing that you have the star that is going to Mars, and the H2 region develops much earlier than the star has reached the final mass, and then it's kind of developing. And then one could think that you have a B-type star that will evolve into an O-type star, and then the H2 region is going to be changing over time.
Yeah.
But then the H2 region associated with B-type stars, they will be weaker, so they will be probably also more embedded, they will be more difficult to detect.
Oh, yeah. But I don't know if you're familiar with the RMS survey. As I said before, this is based on the MSX satellite, so it's far infrared, is not a radio detection at all. But just from the far infrared color, you basically know when there is an H2 region, and it's actually amazingly sensitive. I actually didn't believe it. So, but luckily, you want to go to the website, the RMS website is beautiful, okay? So you click on a source, and what I did, I picked all the lowest luminosity sources they had, because I had a problem initially that I didn't believe that these sources were real. I thought it's too low luminosity. This is like a 6 solar mass stars that can barely ionize, okay? And I thought, really? I mean, and actually detected in the far infrared, it's not even. So I went to the catalog for all the low luminosity sources, and they have all the information, all the Scotch detection, the Scotch survey detection in the radio, and most of them had the radio frequencies that were observed. They're consistent with hypercompact H2 regions seen in the radio, and they have the right luminosity that you would expect from the star of 6-7 solar masses. So actually, so what I'm going to say is that the RMS survey is very sensitive. Above 10 to the 4 or so luminosity, you see the whole galaxy. You're not missing anything. Yeah. But this part, you see a lot here too. And anyway, the completeness correction here is such that, okay, even down to this luminosity, you are completed out to maybe 4 or 5 kiloparsec, essentially. So it's actually easy even for them to make a completeness correction that is pretty well behaved. But I mean, I'm sure this can be improved. The luminosity function, I'm not an observer, and I'm sure that anybody could do a better job than me, but still, you can improve it, but I don't think it's completely wrong. So. There is a lot of improvement there to be made, for sure.
Now that you are in this plot, why these 2 points are gray? They are measurements, no?
Because that's pushing it a little bit, but even Motra Metal in 2011, they said, this is getting shallower here, but you know what? We think is real. They already thought that was real, okay? Because they knew that they were not incomplete there, essentially. There is an extra flattening down here that I don't even fit very well here, because I don't try actually to fit it. And here, you can do better there. So what is the problem? That in order to These are this is the luminosity of stars that can barely ionize. That at 5, 6, 7 solar masses, you have very little photoionizing radiation from the star. And so, but then you have contribution from stars that will become more massive. That at some point earlier on, they were lower mass stars, but those stars have a higher accretion rate based on our model. And so they probably are not compact main sequence stars until they reach maybe 10 solar masses. So actually, they should not contribute to these luminosity beams. So we didn't account for that, for the fact that at the lowest luminosity, you really don't have the contribution of the more massive stars because they're not already, they're not compact structure because the larger accretion rates keep them bloated until they reach maybe 10 solar masses. If we modeled that, then actually we would predict, the model would predict a more, that the luminosity function would get a bit shallower here. And then if we did that, we could try to fit these 2 points. But I didn't want to do that yet. So they're gray because we don't try to fit them, but they're not gray because this is due to completeness. I think this flattening is real.
Thanks a lot for a nice talk. So a question from total ignorance in the field. So probably it's totally stupid. So how sure you are that in your sample of all the stars, especially the high luminosity one, you're actually not seeing binaries that are not resolved? So they would actually go and test low luminosity.
Yeah, I'm not sure.
Straight just because in your
Yeah.
high luminosity there are 2, you don't resolve them.
Yeah.
Because most of the stars are probably mine.
Yeah, yeah. The good news here is that, first of all, no, so not first of all. The short answer is that I don't know, but the other short answer is that I probably know. What I mean is that ALS-III, as I said, is for the all stars, every single one has got spectra from the GOS catalog of 2024. And so I suspect that because they have studied the stars so well and their spectra, maybe they know if they're binary or not. Maybe they're not, but it's possible that a lot of them are binary, and that's the correction that we have to include here. And actually, it's also possible that some of the H2 regions, or likely even, are not powered by a single star. The most massive star will be the dominant one that explains the luminosity because it ionizes more than the low mass stars, but it could be a group of stars, and which goes in the other direction. So are we missing stars here because it should be 2 stars instead of 1? Or actually, are we counting too many of them because here we should put 3 or 4 stars in each H2 regions, and they go in different direction. If I think that each H2 region is powered by 2 or 3 stars, then the estimated lifetime is even longer. If I'm actually missing stars here, this will go up, and the estimated lifetime will be shorter for the H2 regions. So they go in the opposite direction. So, but these are improvements that need to go in the model for sure.
So I have 2 questions. One is, for a given, let's say, 50 solar mass stars or 100 solar mass stars, your model is basically suggesting that most of the mass has been accreted during the H2 region, right?
Yes.
And then, as an observer, my question will be, let's see that we have a sample of 1,000 H2 regions with luminosity between 10 to the 4 and to the 5. How can I estimate which of them are going to still evolve and form a 100 solar mass? Is there a way to observe that? Because you need like a lot of molecular graphs around to keep accreting very efficient.
Yeah, in principle, if you're sitting at this luminosity, you don't know if it is this star, this, or this, right? In practice, the model that we believe that this is being confirmed by the observation, by the comparison of the luminosity function, let's believe that this is true. It tells you that the formation time scales with the square root of the final mass, which means the accretion rate scales with the square root of the final mass, which means that the final mass scales with the square of the accretion rate. So now you can say, try to estimate the accretion rate if it's very large, you're probably going to form a more massive star, which probably coincides with the fact that there is a lot of stuff around, right? But it's possible nowadays that when you have a filaments within some massive star region, that people measure accretion rate or inflow rates from these filaments, you get an estimate. If you get an estimate of the accretion rate, you could claim that you have an estimate of the final mass, because we know both the normalization of these and the exponent, and so you just invert that into, and if you constrain the accretion rate, you basically constrain the final mass that would form in that region. So there is a way, in principle, if you can measure accretion rate properly.
But the accretion rate is constant.
Oh, in this picture, is not. That's the problem. If you look in the yes and no. So on average, is constant. So there is no long-term evolution. For example, it's not like in competitive accretion where it goes like the square root of the mass. The more massive the star, the larger the accretion rate. On average, is constant, but it can have a lot of fluctuation because it's turbulence. So it's the turbulence that decides, do I bring a lot of mass there or not? Do I do it now or later? So there could be large fluctuations. And so as an observer, yes, maybe you're unlucky that you are measuring the accretion rate during a high fluctuation or a very low fluctuation, but you do it statistically, like you said. If you have 1,000 region, you do 1,000 times, maybe not 1,000, but you do several times, and statistically you can try to correlate the accretion rate to the final mass that will be reached by the region.
Yeah, so for the accretion rate in the H2 region, maybe one way to do it is through the recombination lines. Because if this is accretion really, not outflows, the fact that you have a high accretion should have like a larger line with whether or not this is feasible or not.
Yeah.
This may be a naive question, maybe I didn't understand everything, but in all the calculations for the time needed to create a star, how big it is, all that is accounted for is the mass itself, and does the chemical composition of the metallicity also affect this? Is that taken into account?
No, it's not, because all I said is inferred from a simulation of star formation that I call the most realistic to date, because it's huge, because the turbulence is not driven randomly, it's driven by the supernovae. The supernovae are not put randomly, but they come from the evolution of the massive stars, and the massive stars are not randomly. I resolve the formation of every single one of those massive stars. But no, it's not isothermal. But okay, it's essentially isothermal when you go to we compute. It's a supernova-driven simulation, so of course it's not isothermal. But when you in the dense gas, we don't do the cooling and heating and cooling carefully for the molecular gas in the simulations. There is no chemistry, and so that is not given in the simulation. So it's possible that the growth time will be affected maybe by details like thermodynamics or microphysics that is not present in the simulation. However, the whole idea, the picture here is that what drives the growth time of the star is the large scale, is not the microphysics here. Okay, but clearly you have to do feedback carefully. So maybe only half of this mass will be in the final star. As usual, it's not that everything that is going toward the star is going to finish and end up in the star. We know that there are jets and outflows, and there is photoionization, so there is photoevaporation of part of the gas. Not all the gas makes it in. And so the final mass really depends on the amount of feedback that we have studied in detail. So there is a factor of 2 here, roughly, that could be 2, 4, 1.5, we don't know.
The final question is very simple and quick question. After understanding your models, what prevents all these stars from fragmenting as small things?
Because we don't form a massive cores. So as I said before, in this process, the core grows. This is a prestellar core. When the core reaches a Jeans mass, it collapses immediately. I don't form a time at t core of 100 solar masses, which would indeed fragment, in my opinion. That's why I don't think it's a realistic initial condition for the pre-stellar core. And so typically, the pre-stellar cores are between 1 and 10 solar masses, and the stars that you form initially are also between 1 and 10 solar masses. And then they grow. There is nothing to fragment. There is nothing big initially. The flow is fragmented, I mean, because it comes from a turbulent flow. It's very broken up filamentary structures that is accreting onto the central object. It is all fragmented indeed. But some of the mass lands in one point, which is the star. And why is, yeah. It's the seed, yeah.
Competitive acquisition and so on. I mean, if you look, for example, fragmentation around domestic stars, low objects.
Oh yeah, we form clusters. We have like 10 clusters in the simulation. Each cluster has its own IMF. We have a full IMF, in fact, which is a realistic IMF of stars. Yeah, it's like very realistic. The whole simulation, we wrote like 15 papers with this simulation. The simulation took 5 years to develop, then we wrote like many papers. And in each paper, we tried to compare with the observation. We extracted molecular clouds from the simulation and compared with the property of molecular clouds, the line width isolation, the mass distribution, the radius distribution. We have done a lot of comparison with observation that shows that the simulation is really realistic in every aspect that you can compare with the simulation, essentially. And this is yet another one. We can reproduce the luminosity function and the relative slope of the observed luminosity function of H2 regions and of the stars based on the same simulation as well.
Okay, so people answer my question about why from this stars, so then
is what, sorry?
Less high density.
No. We form every star in the simulation. We form low mass stars and high mass stars. They form in the same environment. There is no difference between forming a massive stars and the low mass star. The only difference is this, that sometimes when you form a core, the flow stops there. There wasn't much more coming down. And so you form a low mass stars. Sometimes there is more coming down and the star keeps growing. There is no other difference between a low mass star and a massive star. Turbulence is random. You always accumulate stuff. There's always a region compressing here and there. Some bring a lot of material to a point and form a massive star. Some bring very little material, just enough, just above the Bono River mass, and you form a low mass star. There is no other difference between the low mass star formation and high mass star formation. But there are always smaller seeds, so there is no problem with fragmenting instead of forming a massive star, because you always start from small seeds, which is the reason why you don't find massive pre-stellar cores. You can look for them. You're not going to find them. Now the ALMA IMF project says that there are, out of the whole project, 12 massive pre-stellar core above 16 solar masses. Okay, maybe they're subfragmented. And actually, this is the simulation, sorry. And it's the last question, but this is from the simulation. These are the cores, this is mass versus size. And these are the pre-stellar cores in the simulation. Yeah, they're mostly between 1 and 10 solar masses, but, well, I mean, occasionally there are a few more massive ones. Except you cannot guess the final stellar mass from the mass of the pre-stellar core. And I'm sorry, but that's the reality, okay? So, first of all, I demonstrated in a paper that with ALMA observation, you cannot determine the mass of cores. It's bad news, so the paper doesn't get cited, but it's the truth. We've simulated everything, we simulated the interferometer, you cannot determine the mass of the core. Second, the mass of the core doesn't determine the mass of the star. And so maybe this massive core don't even form massive stars. Maybe this one will form 100 solar mass stars. We don't know at that stage. But in general, you don't form a very massive pre-stellar core because thing has to collapse. Like you said, it would either fragment or collapse, right? So you cannot form massive pre-stellar cores.
So let's Paolo again. We can complete. Muchas gracias.
Nada.
Bye.